started yet. So, welcome everyone. I hope you're having a great time in this game just like I am. And I now have the privilege to take you on a journey. Not just any journey, but a journey of evolving event-driven microservice architecture. Even my intro slides anything to go by, and it's been quite an exciting journey. It started about 5 years ago when I walked into the office, regular day, to learn that we had just sold a 3-month project for a large Dutch bank. All good, right? But it was a huge transformation project to completely overhaul and digitize their lending experience, meaning that clients of the bank could now go online to apply for a loan just by sharing some of their details and transaction history with open banking protocols, and within a matter of minutes, know if they could get a loan in the bank and against what terms. So hugely exciting project, and they said, Oskar, you're going to be the tech lead. So, all right, pretty cool. But I learned that we also made some very, very bold promises to our clients. The first one that we said, we were going to bring this amazing cloud accelerator. So we're going to hit the ground running and start building this digital experience from day one. Now, the truth was that accelerator was built in a different part of Deloitte and we'd never used it before. So, it was a bit of an unknown. But the more bold statement that we actually made was we wouldn't fall into the trap that you commonly see with these 3-month projects, right? Where teams adopt this rapid prototyping mindset. They're just going to build the thing, get it to production, and worry about scalability later. And of course, when the moment of scale comes, you need to re-architect the thing because you cut so many corners. No, we were going to do it in 3 months, scalable, resilient, all the good stuff. So fast and good. So I kept telling myself, everything is fine, while in reality realizing that we would need an absolute miracle to pull something like that off. Especially since many of our engineers didn't have extensive experience with event-driven microservice architectures 5 years ago. Today, different story, but back then it was a super, super big challenge. Now, through the hard work of everyone involved, we actually managed to get it done, so that miracle actually did happen. And not only we got the first version out, but we built on the thing for years, and many engineers of both Deloitte and BBD have worked on this project, so it's been hugely successful. But more importantly for you, we learned quite a lot about how to handle an architecture like this over the years. And I'm here to share those learnings with you today. So you might be thinking, who's this guy? My name is Oskar. I've been a software engineer for about 15 years over at Deloitte. I love writing, but also reading elegant, scalable code, having discussions about architecture and coaching engineers. But I mostly focus on event-driven microservice architecture, so hence here I am giving this presentation. Now, for all of you here today in the Netherlands, feel free to come and chat with me the rest of the day of the conference. We'd love to have a conversation about this topic or any other topic in software engineering. And for all of those dialing in remotely, happy to have a conversation over at LinkedIn. It would be just as nice. Now, I also write blogs on Medium, and to be fair, it's been a while, but there's a couple out there on event-driven architecture that are super relevant to what we're talking about today. So if you want to learn more, that's that place to be. So now awaits me the quite daunting task to condense 4 years of learning into a 35, 40-minute experience that's actually decently okay to follow. So how I will do that is I'll start off by explaining what are microservices for those that are not familiar with the concept to a large extent. Then I'll talk about our project start point, right? So we had 2 weeks to prepare for this massive undertaking. What choices did we make at the time and why? And of course, the final part is when we actually had to live with those choices we made early on, how did that go, and how did we evolve our architecture over time? There we go. So let's explore microservices. What you see on the left side of the screen is what we typically refer to as a monolithic system. A system like this is architected and designed as a bigger application that contains all features that the software system needs. It's often maintained in a larger code base, a single large code base, and deployed to production in its entirety. Now, microservices, on the other hand, are what you end up with when you instead decompose such a system into multiple individually deployable services that communicate over a network and strive to be very loosely coupled. Now, this is what such a microservices could look like. They're often modeled after a certain capability in your system. So if you take digital lending, for example, you have user management, transaction processing, risk calculation, and microservices maintain a cohesive set of business rules or logic that they're responsible for. And more often than not, that logic requires some form of data, which they keep in a database, and they keep that database very private, in contrast to more traditional systems with a big shared database. So why do microservices do this differently? Well, such a shared big database often introduces quite a lot of what we call implementation coupling. There's multiple components talking to the same database. Try changing the database. All those components may be affected. And microservices strive to be loosely coupled, so they keep their database very private instead. Now, of course, they do communicate with each other, right? But they do so over well-documented and versioned interfaces, like their API interface, for example, which they often expose for a front end, like a website or an app to connect to, or another third-party system if you're part of a larger ecosystem. But of course, microservices also communicate with each other. Now, there's a bunch of ways that you could implement that, but the one that I prefer is asynchronous events. And throughout this talk, hopefully, it will become very clear exactly why. Now, hopefully, this helps you a little bit to set us a tone of what microservices are, and let's dive into our baseline architecture, our starting point. How did we try to set ourselves up for success? I'll talk about three different things. First of all, the tech stack that we used on the project, but most of the time I'll spend actually talking about the choices that we made and the complexity that we inherited because of those choices. Now, if you do a 3-month project for a client and you boast about this amazing accelerator that you bring, then you better actually take a look at that accelerator and look at those building blocks that are in there. Now, luckily for us, those building blocks were actually really great. We could easily build Java microservices with the Spring Boot framework. We could deploy them to Kubernetes. We could nicely expose them to the world-fine API gateway. We had our choice of databases, both relational and documents. And last but not least, we had Apache Kafka as the event broker. So we didn't spend a lot of time in those critical 2 weeks that we had to prepare figuring out our tech stack. There was a lot of great stuff already there. So what we instead did is we tried to figure out how would our microservices actually communicate, because there's a bunch of ways that you can do that. Now, in those 2 weeks of discussions and whiteboarding, what we ended up with is that we decided that all communication from front ends towards our microservice would be REST-based, because it's usually request reply anyway, so that should REST incredibly well. We would also use REST communication from our microservice to third-party systems outside of our own system. And that's usually API-driven anyway. But all communication from our microservices to one another would be fully event-driven, asynchronous events. And the reason that we chose to do that is we believe that we could that way build that scalable and resilient system that we promised the client, and also have a system that's very extendable. Now, you don't get all those nice benefits for free when you use events. You have to make some quite critical choices on how you model that event-driven communication. So let's dive into the 3 core choices that we made to make that actually happen. The first and arguably the biggest choice that we made is how we modeled our events. There's different ways that you can do that, and we choose to model them statefully, which I can best explain by an example. If you have a user microservice in your system, your user comes in and updates their user profile, that service would emit a user profile update event or something along those lines. And that event would not only contain the user's actual ID, but also all the data of the profile, or at least the data that just changed. Now, modeling your events this way has 2 major benefits. First of all, your event processing can be extremely performant because all the data is already in the event. So the moment a consumer consumes it, it can straight away do whatever it needs to do. Now, if you instead would use the event notification pattern, where you model your events that only contain the identifier and some metadata on where to get the data from, you have a problem, because now the consumer consumes an event, it cannot immediately do things, it has to reach back to the producer, get the data, and that, of course, cuts your performance potential to the ground. It also makes your event-driven architecture very chatty, which is kind of not what you want, because the more autonomous a microservice is, the better. Speaking of autonomy, the second big benefit that you get from using stateful events is that you could do what we call event-based state replication. And as the name says, the consumer consumes the event, and it can then choose to take some data out of that event and store it in its local storage, especially if the data is critical to their responsibility. It will help them surface future incoming requests. Now, by doing so, a microservice, when serving those requests, no longer has to reach out to other parts of the system to get data. And as a result, your microservice become way more autonomous. And guess what an autonomous microservice gets you if you extrapolate it to a system? A system that is extremely resilient to failures. If you wouldn't do that, you would instead choose to have your microservice collaborate a lot more. what would happen, and this is a simple example, if a client uploads their transaction data to a transactions microservice, if that transaction microservice has to reach out to a user microservice to get data, they have to effectively collaborate together to complete a single request, effectively binding them together. Now you might think, big whoop, what's the big deal? Well, if everything works nicely, everything is up, available, and responsive, you'll have a good day. You're not going to have a good day when this happens. Your microservice goes down and is responsible for a lot of requests. Now, as a result, your whole system's on fire, and you're not going to have the greatest of days. You can argue with me that there's a lot that you can do to make an individual microservice much more protected against going down in the first place, and you should do all those cool things anyway. But by making microservices more autonomous, you will never deal with these cascading failures that are this impactful, right? Things can fail in isolation, which is what you want when you promise your client the scalable resilient system that we promised in the beginning. So stateful events was one way to do it, and we choose to go that route. So once we decided to make our events stateful, the next big decision was, okay, how do we determine what state to put in them, right? There's, again, 10,000 different things that you can do. Now, we adopted the mantra that is quite common in event-driven world that says, don't design your events with your consumer in mind. So put all available data in your event straight away. Don't look at consumers, please. And the reason you do that is that it makes your system much easier to extend down the line. Especially, in our case, we had Apache Kafka as an event broker, so we could do what's called publish-subscribe messaging. Now let's explore publish-subscribe messaging. This is a typical microservice architecture. There's microservices that consume events, but of course microservices have a very focused responsibility, so that they don't care about every event in the system. So they only care about a subset. And they tell the broker that I'm interested in these things going on in the system. Now how that works on Kafka is through topics. Kafka organizes their stream of events through topics, and you can compare a topic to a folder on your file system of your machine. You use folders to organize everything neatly, so you can easily find them, and there's some efficiency there. In Kafka, does the same thing with topics. So a consumer can subscribe to one or multiple topics and get the events that they want. Now, the nice thing is, in this case, it's two consumers, consumer A and B, but it might as well be 10, 100, or 1,000 consumers. The consumers don't care that there's other consumers out there. And the cool thing is, a producer that produces an event, and let's stick with our user profile update example, it will just produce the event, and it doesn't care who's listening there. So pub/sub messaging is very decoupled. Now, if you combine it with the fact that we just chose to put all available data in there, guess what happens? The moment we need to introduce a new feature in our system, it becomes extremely easy. We just deploy a new consumer with that functionality, but it can consume an existing event from an existing topic, so every other part of your system is completely unaffected. Now, if we would have instead designed our event purely based on what consumer A and B would need, guess what? Now, this very simple change becomes a lot more complicated. We have to go back to the event. We need to add the state that consumer C needs. We need to update the producer. We need to deploy the thing. Now, we need to test all the other consumers. It's not what you want on any project, especially not the 3-month one, where you need to get a lot of stuff done quickly. So this was quite a critical choice that we made. Now, the third and final big decision that we made is, how do we tie everything together? How do we create this event flow that represents this beautiful landing experience that we're building? Now, there we have two different patterns. We could have gone orchestration, or we could go choreography. We chose to go choreography. Now, the main characteristic of choreography pattern is that there's no central authority in your system that pulls the strings, tells microservice what to do, and it understands a large part or even the entire system. Instead, choreography is very autonomous. Each microservice knows exactly what they need to do, but they don't understand the broader system. So in this case, the green microservice on the left will know, oh, there's this event happening, I need to do something, and I need to publish an event as a result. So it does one thing really well, but it doesn't care about stuff going on elsewhere in the system. Now, this suited us because it respects the decentralized nature of microservices and the fact that autonomy is very nice. So for us, it felt like a golden choice. Now, you can say, okay, Oskar, with 3 choices, you just built this scalable, resilient, and extendable system. Why is not everyone on Earth doing this? The reality is that there's also a lot of complexity when it comes to event-driven architectures. So I want to also give you a story about complexity. The first complexity, and this is true for any distributed system, is that things need to communicate over a network, and the annoying thing is that the network will fail. Unfortunately for us, Kafka is designed to operate in such an environment, so it deals with that fairly well. So what happens in reality when an event is produced by a producer, Kafka doesn't only store the event on disk, it also acknowledges back to the producer, thank you very much, I got the event. And the same happens on the consumer side. The consumer pulls an event, processes it, and sends an acknowledgement back. Now, this is very nice because if the network fails, it will just be sent again. And we call this at least once delivery. It's very common for event brokers to support this because they're always part of a distributed system. The unfortunate reality is in the at least once. The acknowledgement can also, or the network can also fail on the acknowledgement. So if consumer A gets an event, it processes it, it tries to acknowledge back to Kafka, thank you very much, but the acknowledgement fails. Now Kafka thinks that consumer A never even got the event or it didn't process it properly. So we'll just send it again. Now that can be tricky. So there's two different ways that you could deal with that. You either design your events what we call idempotent, which means that they can be processed over and over again without any side effects in your business logic or your data. So your system will be in the exact same state, regardless if the event is processed once, twice, or 10 times. If you can get away with that, you did yourself a huge favor. Because the only other way to deal with this complexity is by making your consumers aware of the historic events that they consumed. And of course, that comes at quite a big performance penalty, right? It needs to compare the new event against a list of old events, find, oh wait, this is a duplicate, and then simply ignore it because it already processed it. And of course, the longer you make that window, the more impactful those performance implications become. So if you can make your events idempotent, great. But this is a complexity in events that you kind of have to deal with. A second annoying thing to deal with in events is the fact that you build your own consumers and you introduce bugs whether you like to admit it or not. Now, if you introduce a bug, it's possible that your consumer can no longer consume an event. If you do absolutely nothing about this, either one of two things will happen. Either Kafka will retry and retry and retry, and that's in itself not a problem, but if there's a bug, it will never work anyway. And the second thing that happens is it creates congestion, right? There's a line of events waiting to be processed, including events that could potentially still be processed despite of that bug. So you don't want simply to retry things forever. You also don't want to discard events, right? We just have this amazing at least once processing or at least once delivery to make sure we never lose events. So also toss them out the window. What we do instead is what's called dead letter topics. So we create a separate Kafka topic where you can park that problematic event that you are unable to process, and then you can continue to process events as normal. This is a super common implementation in the event world, and many frameworks, including Spring Boot that we use, kind of does it out of the box for you. So that's not really a problem in itself. The tricky bit, though, is that all these failure scenarios, both on your consumer and on the network, make it very difficult to promise that events will be processed in the exact same order they were produced. And again, we were very fortunate to make a flow that was not that strict in ordering. If our events were slightly processed out of order within reason, of course, our system would be just fine. But if you have strict order requirements, things become a lot more complicated. Because some of you that work on Kafka may think, yeah, but there's order guarantees in Kafka, and you would be right, but they're only on a single topic or a partition of a topic, which is like a subhighway within a topic. But we just introduced a second topic to deal with common failure scenarios. So those ordering guarantees basically are just lost, right? And you can regain those by implementing very complex ordered retry patterns. Those exist, so you can actually just do that. But it's a lot of complexity to add to your system. All your engineers need to be aware of the fact that that needs to happen. So again, that's just one of the things that you kind of inherit with events. Now, the third and final thing is not something that you inherit with events, but you do inherit if you do stateful events, and you do event-based state replication, right? You get these enormously cool autonomous microservices, but you also pay a price, right? Because you just copy data all over your system. And of course, you need to be very careful in doing that, but still copies of data are copies of data. So your system becomes what we call eventually consistent. Now, eventual consistency is a concept from distributed databases that basically is a promise in such a distributed database that if you update data, all copies of data stored on different nodes will eventually be updated, and your query will return the same result every single time. Now, obviously, under normal operating circumstances, that window is micro or milliseconds, right? Especially in the distributed database. The second nice thing about the database is that there's database engineers that have spent years and years of their time optimizing for this challenge and shielding a lot of that complexity from you. So I definitely wouldn't hold it against you if you worked with a distributed database before and you were completely unaware that this was even happening. That's the nice thing about other people building your software for you. They also solve your problems. But you just created the problem on a system level, and now you make it your responsibility again to deal with it. So you again need patterns to and make sure to prevent data from getting out of sync. If it does happen, detect it very quickly and automatically make sure that it gets back in sync. So events are extremely cool and they give a lot of benefits, but there's also tricky bits to it, right? So when we had to put our starting point for the project in place, we had to realize that, okay, we need to also deal with these unfortunate realities of an event-driven architecture. So now that we actually had a good starting point for our project, we of course had to live with it over the years. So now we'll actually do the journey part. How did we deal with our architecture over the years? Now, of course, it wasn't all straight away properly done. We had some lessons to learn. And the biggest lesson that we learned was around decomposition. So how do you decompose a system into microservices and how do you do that properly? The second one that we'll talk about was how we later started leveraging the orchestration pattern in our architecture. And finally, we'll wrap it up by some of the moments we had to pivot to introduce greater usability. But let's start with everyone's favorite topic on microservices, decomposition. Almost every team doing microservices struggles with this, and you don't have to search far on Google to find stories of teams that got it wrong. And we, unfortunately, were no exception. We made our microservices too small, like so many others. Now, it's very easy to do because it's actually in the name, right? You call them microservices, which already puts you in a mindset that these things need to be small. Then put on top of it that you hear all these success stories of Netflix and Uber that have hundreds of them, that you kind of think like, oh, if I don't have hundreds of them, I'm not cool. And finally, we also just like looking at a simple, elegant, small code base that is super easy to understand, right? I mean, that's a great day at the office. But all of these things put us in a very naive mindset when we think about decomposition, because we focus too much one-sided on the individual size and complexity of a single microservice. But the unfortunate truth is that you have to, at some point, tie these things together to create a system. And that is when system complexity starts happening. So here you have 6 very elegantly small microservices, but once you tie them together, what you actually get is this, a very difficult system. And it has all these small components that are extremely chatty with each other. The system is complex and difficult to live with. Now, this is an example that I make the proof of point. We didn't do something near this extreme, fortunately, but we still went too small. Now, the problem with decomposition is it's very complex and nuanced. So every project will have different ways to decompose, and there's no right answer for everyone. But there's 3 things that we learned that I think are critical enough to share with you today. So the biggest thing that we did is we flipped our mindset. We didn't start decomposition by setting the smallest possible boundaries. We adopted the widest possible boundaries, right? And that's quite fundamental. And we also realized that making decomposition decisions early on in your project is the absolute worst thing that you can do. Because at that point, you're in the worst possible point to make a good decision, right? It's a new client, it's a new environment, it's a new system. You don't really know how the system is going to evolve, where complexity is going to rise. You just don't have the tools to make a good decision yet. So if you can keep those wide boundaries in the beginning, then please do so. Of course, you still need to apply proper software design by thinking about coupling, about cohesion, and how you make the software component modular. And if you do that well, then carving something out into a microservice later is not that big of a deal. So, but doing it later, again, you have more knowledge to make proper decisions. So that's very important. Now, the second thing is I started seeing commonalities between microservices that are too small, making it much more easy to spot if you've gone too far already. The first one is if you do state replication like we did. If you have almost complete copies of state in multiple places in your system, you might be looking at candidates of services to merge back again. So if you, for example, have an email microservice that just copies the user's email name, that's completely fine, right? There's nothing wrong with that. But if you have 2 or 3 entire copies of your user data in your system, there has to be a reason for that. And more often than not, the reason is that those services operate on the same concept that cohesively should be inside a single service. And merging those back together will greatly reduce not only your system complexity, but also those annoying data synchronization complexities that I just talked about. So do yourself a favor and have a hard look at that. But even if you don't do state replication like we did, if your microservice in general has more integration-related code, so code it needs to interact with the rest of the system, than actual functional code, so what the microservice is supposed to do, then it's very likely that you've made them too small. Because if it needs more integration code, it's very chatty with the rest of the system, which usually meant that you pulled concepts apart that cohesively belong together inside a single component. And again, looking at those and trying to merge them back together could greatly reduce the complexity of your system overall. Because again, I cannot stress, and you have to experience this to really fully realize it, because you can read all the war stories online if you want. But if you're in a place where your system has too much small services, it just becomes very difficult to live with. This impacts every single stage of software development, from your design, your coding, your testing, your deploying, everything. It really takes a big toll. So don't go too small. The nice thing though, that you see a bit of a pivot now in the industry. You see prominent engineers, for example, over at Uber saying, we call them well-sized services now, not microservices, to get away from that obsession over size and quantity. You also see much more balanced conversations nowadays that microservices are not some magical cure, nor are they an architecture that everyone should use, because it's a complex architecture. It has its place, but it's not the starting point for all projects. It shouldn't be. And finally, you see, as a result, also more conversations happening that good software design, just looking at coupling and cohesion and how to apply modularity, is way more important than any architecture. If you're struggling maintaining a monolithic system, simply converting it to microservice won't solve the inherent design flaws that it has. You will just have poorly modeled microservices, which we often call nowadays a distributed monolith, which is actually even worse to live with than a monolithic system that you were so worried about. So take your time with proper decomposition, apply good modularity principles, and please don't go too small. Biggest lesson that we learned over the years. The second lesson that we learned was that in the beginning, of course, your system is fairly simple, right? You have a lot of, if one thing happens here in the system, then this other thing needs to happen here. And that suited choreography pattern very well. But we started having more and more interaction where three things need to happen, then this one thing needs to happen, and then this other thing needs to happen. So your flow becomes more complex. Now, at that point, we found ourselves at a bit of a crossroads. Do you continue using the choreography pattern exclusively? And we could have. Right, you could implement that, but you basically create mini orchestrators at that point that understand a small part of the system very well. And we could have done that because it will still have a nice level of autonomy and decentralization. But we were also struggling with a system that had too many small microservices. And if you combine those two together, one, your application flow is smeared out over a lot of different services instead of centralized, and your microservices are too small, your system just becomes very difficult to understand. And it started slowing us down as complexity started to go up. So we decided we're going to pivot. We're still going to do choreography pattern where it makes sense, but we're also going to use the orchestrator pattern to orchestrate our flow. So, and at that point, we also started looking around a bit more what's happening in the market, what are Netflix and Uber doing. Again, we're not arrogant enough to think we're Netflix and Uber. We have nowhere near the scale or the complexity. But we can still learn from them. And we learned that they extensively use the orchestrator pattern and even open source their own engines to support this pattern. And Netflix has Conductor and Uber has Cadence, and there's probably a bunch more. But it's really strengthened our resolve that centralizing some elements in your architecture doesn't mean that you can't scale anymore, right? We always think, oh, bottleneck, oh, single point of failure. But in reality, it's not really that black and white. And if Netflix and Uber can do it at scale, then we can probably also do it. So we figured, let's give that a try. So we rebuilt our architecture, but we did it slightly different than Uber and Netflix. Uber and Netflix have a very traditional implementation of the orchestrator pattern with a very strict separation between flow logic, so how does your application flow, and execution of business rules. They keep it very separate. But because we were struggling with a system that was very difficult to understand with many different services, we decided to go a different route. We did this. We merged those two responsibilities into one component. Again, we widest possible boundaries instead of smallest. And the reason we did that is that it allowed us to greatly simplify our system and create this component that was basically the brain of our flow. And it decided what needed to happen in which order, but also the business rules inside it, not all of them, but the majority of them, all resided in a single component. And as a result, our system became so much more easy to understand and work with that we were able to achieve much greater speed while complexity was still increasing. Now, of course, we still very much had an event-driven microservice architecture because we had microservices that did transaction fetching and processing, risk calculation, sending out emails, sending out offers. But we choose to centralize some big responsibilities in that component. And it helped us really well. And it helped us for at least like 2.5 to 3 years that we benefited greatly from this pattern. But of course, like any good decision, at some point circumstances change. Now, not only did we have more and more teams working on this system, making it more difficult to organize around larger components, right? That's also what a lot of monolithic projects tend to have difficulties with. But also, we were now not only designing this beautiful learning experience for customers anymore, we were also building applications for the employees supporting those customers, which is of course very cool, right? And they were helping them closing the loans, they were doing all the regulatory maintenance on existing loans. But that gave us a problem, and again, we found ourselves at a crossroads. Do we put that all in a single orchestrated component? And we didn't feel comfortable doing that. That's a lot of complexity for a single component. If you have 7 or 8 teams working on a system like that, it just becomes very difficult to organize that properly. So we decided, okay, let's at least have one orchestrator for the customer-focused journeys and one for the employee-focused journeys, right? Keep that separate. And that gave us a second problem, because guess what happened to those business rules? Some of them needed to be in both, of course. So we're not going to copy willy-nilly business rules all over the place because you want to keep those absolutely in sync. So we decided to pivot our pattern back to what is a more traditional orchestrated pattern with that clear separation between your flow execution as a whole, right? So which step do you take in which order, and the execution of the business rules that make that thing happen. Now, we of course didn't want to go back to simply having super small microservices again where they have a couple of rules. So we took a bit more time now, and luckily we already applied proper modularity in the bigger component earlier. So we had sort of cohesive set of rules that we could carve out one by one. So we transferred away from this one by one into this pattern. Now this pattern we live with today, and it's a really good pattern. I think this is the sweet spot that we finally found, where the system is still fairly easy to understand because we have this orchestrator that contains most of the business logic. We have amazing reusability because we carved out the business rules so they can be used by multiple orchestrators if needed. It does require a bit more good engineering to make sure those rules are agnostic of all the different flows that they're part of, but it serves us really well. So we are now at the place where we also have what Uber calls well-sized services, right? They're not too small, they're not too big. So I really think that we hit the sweet spot finally after adapting a couple of times. Now, of course, this all happened over the scope of 4 years, so it isn't like we pivoted from left to right and back overnight. And I also think that it's not unrealistic to pivot a couple times if circumstances change, but that maybe just me coping with his story as well. But yeah, this was the journey that I wanted to share with you today. It's been an incredible experience, to be honest, with all the engineers from Deloitte and BBD. I mean, I love having conversations with teams on architecture and topics like this and seeing how everyone cares about creating software that's as simple and easy to understand as possible, and they really, really deeply care about the internal quality of the software they deliver. So not just what the client sees, because of course we all care about that, but also that the engine that's actually providing that experience is to the best that it can be. This was an exceptional project that I'm very proud to have been a part of, and equally proud to share with you today on everything that we've learned. So unfortunately, that kind of concludes our journey, which makes me sad. But yeah, it's been an amazing experience. So hope you took away some key learnings for your own projects, and hope you give event-driven architectures a try because they are really great if you do them right.